Hi guys, welcome to another lecture in the series Organic Chemistry 2, and today we're going to be talking about ultraviolet and visible or UV-VIS spectroscopy. Alright, so for UV-VIS we're talking about wavelengths in the 100 to 400 nanometers for ultraviolet and 400 to 800 nanometers for visible. So what happens when a molecule absorbs AMR in the UV-VIS range? Well, an electron is promoted from one molecular orbital to another molecular orbital of higher energy. So today we're going to be looking at answering this question. How can we use the data which we obtain by measuring absorption by molecules of UV-VIS radiation? All right, so the molecular electronic levels that we're talking about, and as we can see the scale over here in terms of energy, so these are lower energy, these are higher energy. So we have our sigma. So if you have a molecule with single bonds, they have electrons in sigma, overlapping of orbitals forming a sigma bond. And then you have, pi bonds, and you have non-bonding electrons, and these contain lone pairs of electrons. So when you have oxygen, nitrogen, for example, they have non-bonding electrons and they're higher than the sigma and the pi in terms of energy. And we have our antibonding orbitals, molecular orbitals, pi star and sigma star, and they're usually vacant in the ground state, and these are usually occupied levels. So the most feasible transitions are from the highest occupied molecular orbital, or HOMO for short, to the lowest unoccupied molecular orbital, which is LUMO for short. Alright, so in terms of Huckel molecular orbital theory, when you have a molecule such as methane with only single bonds, which means it has sigma bonds, right? So you only have sigma and sigma star molecular orbitals. And then when you have a molecule like methanol, where you have sigma or single bonds, and then you have an element such as oxygen, where you have these non-bonding electrons, then that's when we have N come into play. And then when you have a molecule with a double bond like ethene here, we have a mixture of single and double bonds. So we have the appropriate molecular orbitals here. And then when you have a mixture of all of them, that is single bonds, double bonds, and elements which have non-bonding electrons, then we have all of the above that we mentioned. All right, moving right along. All right, so what are the possible transitions? So for alkanes, the possible transitions are sigma to sigma star. For carbonyl compounds, and you see that occurring twice, you can have sigma to sigma star transitions, as well as N to pi star transitions. And then for your alkenes, your alkynes, and carbonyls, again, you can have pi to pi star transitions. And then for compounds containing non-bonding electrons, such as oxygen, nitrogen, sulfur, or halogens, you can have N to sigma star, as all of these being possible transitions for these types of compounds. All right, so let's start by looking at various types of molecules to see what are the possible transitions. So here we have methanamine, or you might see it as methylamine. And if we just draw out the structure here to identify the types of bonds that we have, we will see therefore that we have sigma bonds and we have non-bonding electrons, right? So that therefore means that in the case of HOMO to LUMO for this particular compound, the transition would therefore be from N to sigma star. So in a given system, it is the transition from the lowest energy from the highest occupied molecular orbital to the lowest unoccupied molecule, so from HOMO to LUMO, which is usually the most important. So even though there might be other occupied levels, right? What we're looking at is the highest occupied molecular orbital, which is HOMO, and the lowest unoccupied molecular orbital, which is LUMO. So for this molecule, methanamine or methylamine, or HOMO, is, or represents the highest energy, the highest occupied molecular orbital, which is N. These are our non-bonding electrons. And then so the transition that we would see here is from N to sigma star. All right, so selection rules. They are theoretical restrictions based on the differing symmetry properties of orbitals and changes in spin quantum number. So on the basis of selection rules, certain transitions are formally forbidden. So the N to sigma star is one such forbidden transition. So despite being forbidden, the N to sigma star transitions, they do occur, but with low probability. All right, so looking here at another molecule, and we don't have to draw this one out because we can clearly see that we have a double bond here and we have some single bonds, right? So in this case, our HOMO is definitely or electrons in our pi bond here, right? Because that would be our highest occupied molecular orbital. And so in this system, the HOMO to LUMO transition is pi to pi star. All right, so for another molecule, which is propane, so it is an alkane. So clearly we only have single bonds, and if we only have single bonds, then in this system the HOMO to LUMO transition is sigma to sigma star. The change in energy for this transition is actually very large. So as we can see here, from sigma to sigma star, that change in energy is very large. And because it's very large, and we should be familiar with this equation from other spectroscopy topics that we looked at, right? So the change in energy is directly proportional to the frequency and is inversely proportional to the wavelength. And so high frequency short wavelength radiation is required to cause an electron to move from sigma orbital to sigma star orbital. And so the lambda max for propane is approximately 135 nanometers. So you want to have a general idea of the approximate lambda max for various functional groups. So for molecules such as these alkanes, they fall in this relative region. So this AMR is in the vacuum UV region. These absorptions are not analytically useful. All right. So compounds containing elements with non-bonded, and that's N electrons, that is oxygen, nitrogen, sulfur, halogens, which I mentioned already, they undergo N to sigma star transitions. the change in energy for N to sigma star transitions is less than the change in energy, and that is from here to here, right? It's less than the change in energy from here sigma to sigma star transition. And molecules containing non-bonding electrons absorb EMR in the ordinary UV region that is greater than 180 nanometers. So again, we just need to have a general idea of these numbers. All right, so as we mentioned a while ago, for our non-bonding electrons, they absorb in the ordinary UV region, lambda max being greater than 180 nanometers. So these are examples of those types of compounds. So we have methanol, triethylamine, and iodomethane here. And these are the lambda max for these compounds. So as we can see, all being greater than 180 nanometers. So most organic compounds containing elements with non-bonded electrons will exhibit some absorption near 200 nanometers. This is usually called end absorption. All right, so that leads us to our first question, which is suggest a reason why triethylamine in acid does not show absorption due to the N2 sigma star transition. So take a second and think about it. All right. So if you thought about it and you came to this conclusion, then wonderful job. So for triethylamine, we have our non-bonding electrons here, and in the presence of an acid, it will therefore become protonated. And so the non-bonding electrons are now involved in a dative covalent bond, and therefore that transition will not be observed. So they are no longer free and able to participate in that transition. And so that is the reason why when it is in acid, it does not show this particular transition. All right. So continuing on, looking at the various lambda max for the various transitions, here we're looking at N to pi star and pi to pi star transitions. So compounds with double and triple bonds, as seen here, undergo N to pi star and pi to pi star transitions. And so the change in energy for these transition is much less than the change in transition for or sigma to sigma star, as we have seen, and the N to sigma star transitions as we have also seen. And so aldehydes and ketones, they undergo N to pi star transitions, and the lambda max for these N to pi star transition is approximately 275 to 295 nanometers. So essentially you want to have this relative scale or this one in mind, just to have an idea of the relative, well, maybe not this one, the one with the nitrogen, right? So we have a general idea of the energies, relative energies of all of our bonding and antibonding molecular orbitals. All right, so chromophores. Chromophore is a term used to describe any system containing electrons which undergo transition on absorption of UV-VIS radiation. Most simple unconjugated chromophores absorb high energy, short wavelength radiation and are not analytically useful. And we have a few examples here. Important chromophores are conjugated systems. So when we speak about conjugated systems, we're talking about when you have a system such as these here, where you have a carbon-carbon double bond followed immediately by a single bond, a carbon-carbon single bond, and then followed immediately by X here. So X here could be oxygen or it could be another carbon, and this chain of course can continue. So anytime you see or hear conjugating, we're talking about alternating single and double bonds. So double, single, double, single, etc. Right? So here we have double, single, double. We have double, single, double, and if it's extended it will be single, double, single, double. So these are the important chromophores. The unconjugated chromophores and the simple ones, they are not analytically useful. All right, so let's look at, as we have done with other spectroscopy techniques, let's look at the fundamentals of obtaining a spectra. Sure, you know this already: singular spectrum, plural spectra. To obtain useful information from a UV-VIS spectrum of a compound, the wavelength, which is the lambda max. So I have been quoting the lambda max numbers for various transitions and correlating that to particular types of molecules, you know, whether or not they have single double bonds or non-bonding electrons. So this is very important: the wavelength, the maximum wavelength, and the intensity of absorption must be measured accurately. So this measurement is most commonly carried out in solution, and the solvent is therefore very important. And most times when you quote the values, you generally put the solvent because that is important as well. So the solvent in which a UV-VIS spectrum is being determined must not absorb light in the same region of the spectrum as a compound under investigation. And that should make sense, because if you're trying to figure out a particular lambda max for a sample and your solvent absorbs in the same region, then you won't be able to distinguish between the two. So the solvents most commonly used for making solutions for determination of UV-VIS spectra are 95% ethanol, water, and hexane. So the cutoff point is important, and by cutoff point we mean that we cannot have interference in terms of the solvent and the sample where they absorb UV light, right? So the cutoff point means that below that particular wavelength, that is where the solvent absorbs. And so after that point, everything that we see should be related to the sample and not the solvent. So there is that point where we can therefore say, okay, this portion is directly related to the sample and not the solvent. All right, so the compound under investigation, which we shall call the analyte, is weighed accurately and a solution made up in a volumetric flask. And this, I'm sure you know what a volumetric flask looks like. A small quantity of the solution is then placed in a cuvette, as seen here. A container approximately 5 cm high and usually 1 centimeter square in cross section. The material of which cuvette is made must be transparent to the light in the region being studied. And you might see glass being used as a material. Is transparent to visible light but absorbs UV light, or you might see quartz as a material being transparent to both visible and UV light. So again, you don't want any interference from your solvent. In the same vein, you don't want any interference from the cuvette. All right, so the cuvette containing the solution is placed in the UV-VIS spectrophotometer. In the spectrophotometer, there are usually two lamps. So one as a source for UV light and the other as a source for visible light. So the hydrogen discharge lamp is usually the source of the UV light, 180 to 400 nanometers, and the tungsten filament lamp is usually the source for the visible light, that is 400 to 800 nanometers. So mechanisms within the spectrophotometer enable scanning of the range of wavelengths. So that is from the UV to the visible portion, and measurement of the intensity of transmitted light. So in the determination of UV-VIS spectra of solutions, the effect of solvent is removed by measuring the absorbance of the solvent using a cuvette containing solvent only. So the spectrophotometer can electronically subtract the absorbance of the solvent from the absorbance of the solution, right? So at the end of the day, the spectrophotometers usually provide a plot of absorbance, which is on the y-axis, versus wavelength, which is on the x-axis, and it looks like this. And we've been talking about lambda max, so it usually shapes like this. The data from the spectrophotometer, and the output is usually like this, and essentially the lambda max is the highest point, and it corresponds to a particular wavelength. Here in this case is about 217 nanometers. So as I said, we have been quoting lambda max values. So this is the maximum absorption at this wavelength here. All right, so the Beer-Lamberts law. I'm sure you know about this law and this relationship here. That is A is equal to the molar extinction coefficient times the concentration times the path length, right? So A, which is the absorbance, also called the optical density, and you might see epsilon being quoted here as well, and that usually refers to the intensity of the peak. So we'll see that, or some relative values for that in a little bit. And of course, their concentration, mole per dm cube, the path length, that's usually 1 centimeters. So essentially here, this is an important relationship to remember, that is absorbance and how it's related to the concentration as well as the path length and epsilon. All right, so molecular orbitals and molecular orbital energy levels. So here we have various compounds here in this column, and their associated wavelengths and their intensity, which is, you know, the epsilon value. So we can look at these values to know whether or not it was intense or not. The transition with lowest energy seen here. So we have various transitions, and we've spoken about these transitions generally, right? So this table is really just for you to have, you know, a general idea of various compounds, their wavelengths, and, you know, which transition is responsible for that. And also just to show you the typical absorption of simple isolated chromophores. So, you know, there are various classes of compound, and their related transition and their lambda max in nanometers their relative intensity, and we have some other compounds and the same type of information. So again, essentially you should be able to look at a table like this and understand how to, get information from it. What is it trying to say? What does it mean? All right, so let's see if we can use that information with this question. Which chromophores and transitions give rise to the absorptions shown in the following compounds? So we have cyclopentene at 190 nanometers, triethylamine 195 nanometers, 3-octene 185 nanometers, ethane 150 nanometers, and dimethyl ether at 185 nanometers. So what you want to do is to just try to draw these compounds and then essentially tell me which transition give rise to the wavelength seen here. So pause, try to answer it before you listen to the answer. All right, so I went ahead and drew, these compounds. So hopefully my answer is similar to what you had. So for the first one, which was cyclopentene, we have one double bond. So in the cases where we have one double bond, we have the pi to pi star transition. Where we have only single bonds, we have sigma to sigma star. Here we have, non-bonding electrons. I should have placed them in for my oxygen. So we'd have the N to sigma star transitions there, and similarly for triethylamine. All right, so now we're going to look at some terms used in UV-VIS spectroscopy. So you've seen lambda max a number of times now, and that's the wavelength of maximum absorption. So we know that that wavelength is inversely proportional to the change in energy of the electronic transition. Chromophore is another term, which is the system containing electrons which undergo the HOMO to LUMO transition. Substituents that increase the intensity of the absorption and in some cases the wavelength. And so, this basically any system containing electrons which has a HOMO to LUMO transition. Another term, oxochrome, which is a substituent which changes a chromophore to produce a new chromophore. So here we have, ethene, which is chromophore. So it has a lambda max of 190 nanometers. So one of the hydrogens were replaced by this amine group here, and therefore they're formed a new chromophore with a new lambda max of 230 nanometers. So it's a oxochrome, which is a substituent which changes a chromophore to produce a new chromophore. All right, some other terms used in UV-VIS, bathochromic or redshift, hypsochromic or blue shift, hypochromic shift, hyperchromic shift. So that's up, down, left, right. Right, so that is for the lambda max. So this is the wavelength here versus absorbance. So when you have a shift to the right, to the left, up or down, these are the terms that are used. All right, so just going to the definition further for our bathochromic shift, and just going back to the diagram, that shifts to the right here, which obviously means an increased wavelength, right? So a shift of an absorption maximum to a longer wavelength caused by either a change in medium or the addition of an oxochrome. So an example of a bathochromic shift caused by a change in medium is seen here. So we have phenol in alcohol, and this of course is phenol. And when you add base, that is 1 drop of 5% potassium hydroxide in methanol, you get a phenoxide ion. And as we can see here, the lambda max increased essentially, right? And the intensity, as is referenced by the epsilon or the molar absorptivity value, that we show an increase from 6,200 to 9,400, that has increased as well. So the intensity and the position of the lambda max has increased. That is as a result of adding a drop of base. So that would be referred to as a bathochromic shift or a red shift. So a bathochromic shift also results from an increase in the length of a conjugated system, that is a decrease in energy required for excitation. So we're gonna look at some of these values in a little bit in terms of the bathochromic shift for a conjugated system. So we referred to oxychromes being one reason why you might have a bathochromic shift. So many oxychromes exert their bathochromic shift by means of an extension of the length of the conjugated system, especially those with unshared electrons on the atom attached to the double bond system. So resonance interaction of the lone pair increases conjugation. All right, so as we can see here, we have a double bond and we have, our oxygen here. So our lone pair can basically form we can have two canonical structures here, because showing the delocalization of electrons, where we can form a double bond here and form a negative charge here. So the resonance here basically shows some type of increase in conjugation, and therefore that would cause a bathochromic or red shift. In terms of your hypsochromic shift or blue shift, that is a shift of the lambda max to a shorter wavelength, so that's moving to the left, usually caused by a change in medium. An example of a hypsochromic shift is seen here. So for aniline in ethanol, if you add acid, and we looked at this earlier, the amine will be protonated to form the anilinium ion, and so the lambda max now moves from 230 nanometers to 203 nanometers. And so the conjugation of the lone pair on the nitrogen with the pi system of the benzene ring is removed when hydrogen is protonated. So we don't have to spend any time on that because we looked at a similar example. All right, so let's look at the UV spectra of alkenes, the effect of conjugation. So here we have, alkene, a typical alkene, which is ethene, and then in the middle we have a conjugated system. So we have a double bond, a single bond, and a double bond. And the lambda max here being 217 nanometers, as opposed to lambda max here being 120 nanometers. So the HOMO to LUMO, of course, would be pi to pi star here. That is X. Right? So for this molecule, and it's color coded depending on the molecule that we're talking about. And so for the simple alkene, this is the change in energy between pi and pi star, which is X for this molecule. For when you add, so for the new molecule, we added basically another double bond, right? So a single then a double bond. So as a result of that, now we have a new HOMO and a new LUMO, so highest occupied molecular orbital, lowest unoccupied molecular orbital. So which is now Y, which is, we can therefore see the change in energy is very much different for the alkene, the simple alkene versus the conjugated alkene, right? And as a result of that, the lambda max here is 270 nanometers versus the 190 nanometers in the typical simple alkene, or unconjugated alkene, I should say, right? And then for you know, the similar alkene, we can see here that the homo to LUMO transition here would be similar to over here being the same molecule, right? So the point we're making here is that when you add, when it's now a conjugated system, you have a new HOMO and a new LUMO, and that change in energy is much different. There's a shorter, the change in energy is much less when you have a conjugated system, and therefore that is reflected in the wavelength, which is 270 nanometers as opposed to 190 nanometers. So in the series, a change in HOMO to LUMO, as we said, decreases with increasing conjugation, and so the lambda max increases by approximately 30 nanometers with the addition of each double bond to the conjugated system. So here, as we saw with our simple alkene, that lambda max is 190, and every time we add another double bond, it increases by roughly 30. The lambda max increases by approximately 30 nanometers. So 90 plus 30 gives us 220 nanometers, plus 30, 250, plus 30, 280. So each time we add a double bond, we extend the conjugation. So this is 2 double bond, 3, and 4. So lambda max also increases by approximately 5 nanometers with the addition of each alkyl substituent to the conjugated system. So let's look at an example here. And these are considered to be Woodward rules, and this is how we apply it. So we have a base value of 240 nanometers for a conjugated diene as seen here. So when we have a molecule like this, the conjugated diene base value is 240 nanometers. We have two alkyl substituents, one here and one here, and as we said here, the lambda max increases by approximately 5 nanometers with the addition of an alkyl substituent to the conjugated system. And so we have two alkyl substituents, and so 2 times 5 gives us 10, and we add that to the base value and we get the calculated lambda max as 224 nanometers as opposed to the observed lambda max of 226 nanometers. So essentially what they did, they came up with a bunch of rules for getting a calculated value for the lambda max, and it worked out to be very close to the observed value for lambda max. So another another type of addition that we need to know how to find it is the double bond exocyclic ring. So this is when you have a ring and you have a double bond that is outside of the ring, and it's and this type of arrangement is called a double bond exocyclic ring. One of the sp2 carbon atoms of the carbon-carbon double bond has to be a part of the ring. And so let's see how we calculate the lambda max for these two compounds here. So firstly, we pick out our conjugated diene, which has a base value of 240 nanometers. So here we have our conjugated diene. And then we can see we have two alkyl substituents. And in the same fashion as above, we multiply that by 2 times 5 nanometers, and we add it all together, and we get the same value as we got up here. So clearly we're looking at alkyls attached to the conjugated diene and nothing else. So we're not counting anything else. All right, so let's look at another molecule. So here we have this conjugated diene with the same base value. In this case, we have two alkyl substituents as well, but they're on the same carbon. And we're also adding 5 nanometers for one exocyclic carbon seen here. So because we have the double bond being exocyclic, we're adding another 5 nanometers. So if we add them all up, that is 214 plus 10 plus 5, we get 229 nanometers for this molecule. All right, so some other things that we need to know and some other terms, and this is Woodward combining with Pfizer to create another set of rules with regards to homoannular dienes and heteroannular dienes, right? So when you have the dienes still conjugated and in a ring, or two rings seen here, but they're in the same in the cis arrangement, the base value is 253 nanometers. However, when they're in the transoid, this is cissoid arrangement, cis on this, same ring. When they're in the transoid arrangement in the form of the heteroannular diene, the base value is now 214 nanometers. So for our homoannular dienes, our base value, so we're going to do the same as we did previously with these homoannular dienes and heteroannular dienes. We're going to do their calculated lambda max and then compare it with the observed lambda max. All right, so here we have a homoannular diene and the base value therefore is 253 nanometers. So we add to that 4 alkyl substituents, that is 1, 2, 3, and 4. So we multiply that by 5 nanometers. We have 2 exocyclic carbon double bonds. So here, this is one, so we have a ring and we have a double bond on the outside. We have another ring and a double bond on the outside. So it's 2 of them. So 2 times 5 gives us 10. We add them all up and we get 283 nanometers, and that is very close to the observed lambda max. All right, so let's go ahead and do the same calculation for the heteroannular diene seen here. So as mentioned up here, the base value is 240 nanometers. In this case, we have 3 alkyl substituents, one here, and one here. We have 1 exocyclic double bond, so clearly this double bond is not exocyclic, so this one would be the exocyclic double bond, and we only have 1 of such, and so we add these all up. And we get 234 nanometers, which is exactly the same as observed lambda max. And then finally, when you have a mixture of the homoannular and the heteroannular, the homoannular diene is used as the base value, which is 253 nanometers. And then in this case, we have the double bond extending the conjugation being 30 nanometers. And we have 5 alkyl substituents, so let's count them. So along the entire chain of double bonds here, So we have one, 2 here, and then 3 here, and then 4 here, and 5 up here. So as we can see, this carbon is counted twice. So it's counted because it's attached to this carbon here, and it's counted again because it's attached to this carbon here, right? So we count all of the alkyls along the chain. All right, so that is well, continuing our addition. So we have our double bond extending the conjugation 30 nanometers. We have our 5 alkyl substituents, so that's 5 times 5 nanometers. We have 3 exocyclic double bonds, so let's see if we can find them. So we have one here, we have one here, and we have one here. So it will take you a while to get the hang of it, but trust me, you will, right? So it's just to tune in to, you know, understanding how to look for it. So we basically add these all up and we get 323 nanometers as the calculated value, and that is extremely close to the observed lambda max of 324 nanometers. All right, so again, you know, these are the rules in a table for our homoannular cissoid and our heteroannular transoid, and we have our base value, and we just add increments for whether or not you have a double bond extending the conjugation, you have an alkyl substituent or ring residue, an exocyclic double bond, and other things, you know, added to them, and you just add them all up and we get the calculated lambda max. All right, so we have another question. A liquid compound of unknown structure has the formula C5H8. The UV spectrum shows a lambda max at about 220 nanometers. What are 2 possible structures of this compound? So you really have to, you know, try to give it some thought here. So take a second, pause, and try to answer it before you listen to the answer. All right, so firstly, you want to calculate the DBEs, right? So I don't have the formula for it here, but you should know it based on previous lectures. So you want to calculate the DBE, and it works out to be 2, which should tell you that you have, so that information in combination with the fact that you have a lambda max of 220 nanometers should tell you that you have some type of a conjugated system. So if we have 5 carbons here, then we can go ahead and draw 5 carbons, 1, 2, 3, 4, 5, and we can draw them in a conjugated way. And, you know, this is another possibility of, you know, having the same molecular formula. So let me know if you agree or if you have something different that might match the data. All right, so let's look at the UV spectra of carbonyl compounds. So in carbonyl compounds, there are 2 types of electrons which can readily undergo transition on absorption of UV radiation. So pi electrons and N electrons on oxygen. So the HOMO to LUMO transition is N to pi star. So this transition gives rise to a lambda max, which is 275 to 295 nanometers. This is a symmetry forbidden band, and therefore epsilon for this absorption is very low. So in other words, the intensity is low for this transition. All right, so similar to, like a typical conjugated compound where, instead of having oxygen here, instead of having carbon here, we have oxygen, right? So this compound is an ene-one because you have the ene part is the carbon-carbon double bond, and the one part is the carbon-oxygen double bond. So it's an ene-one, and the lambda max is roughly 215 nanometers. So here you have a typical double bond, and when you extend the conjugation, again you have a new HOMO and a new LUMO, and the change in energy there between these transitions is now much less. So when the carbon oxygen and the carbon carbon these double bond, these chromophores are brought together, the molecular orbitals interact to form molecular orbitals of higher and lower energy as shown above here. And so we have two bonding orbitals, pi 1 and pi 2, seen here, which has electrons, and one antibonding orbital, pi 3 star here, which is our new LUMO. And so the change in energy for pi 2, as seen here, to pi star 3 is much less than the change in energy for typical pi to pi star. And that is synonymous to what we saw earlier. So we have a set of Woodward rules for predicting the lambda max of conjugated carbonyl compounds as seen here. So our base value is 250 nanometers, and here we have two beta substituents. So this is our base value would encapsulate this portion of the molecule, and then our beta, we count what is attached to this alpha carbon here and this beta carbon. In this case, we have no substituent on the alpha carbon. Here we have two substituents on the beta carbon, and so that's why that's 2 times 12 plus the base value. Add them all up and we get 239 nanometers, which is extremely close to our observed value of 237 nanometers. So when we, continuing on that, it's important to note that this attachment, if we have an alkyl here, it doesn't count. What counts is what is attached to. Well, we'll soon see in the slide coming up after this. But let's do the calculation for this compound. So our conjugated enone base value is 250 nanometers. We have two beta substituents, which is 2 times 12 nanometers, so 12 per beta substituent. We add them up and we get the same value as before. And also for extending the conjugation, it's similar to what we saw with our diene, where every time you extend the conjugation, you add 30 nanometers to the base value, and this doesn't count as an exocyclic double bond, right? So the exocyclic double bond is basically, when you have a carbon-carbon and not a carbonyl, right? So this doesn't count as an exocyclic double bond. And this is our base value for our conjugated enone. All right, so these are the empirical rules for the enone. The base values, if you have a 6-membered ring or acyclic parent enone, that is 250 nanometers, as we have seen. If you have a 5-membered ring parent enone, that's 205, etc. and you add increments for double bond extending the conjugation, sorry, as we saw, 30 nanometers for your alkyl group or ring residue. So if you have an alpha substituent that is 10 nanometers, and we saw the beta one, so this is our enone or base enone. As we said, this one does not count. The alpha counts, but that's a 10 nanometers addition if you have an alkyl group or ring residue. If you have beta, as we saw already, that's a 12. Gamma, so that is, sorry, gamma, delta, gamma or higher, you add 18 nanometers, right? So hopefully this image is a little bit clearer, gives you the alpha, the only, well, two new information here, the alpha residue increment, and if you have, you know, an extended conjugation, to how to add your alkyl groups to it. So it's 10 if it's alpha substituent, and gamma and higher is 80 nanometers. And or exocyclic double bond is still 5, right? So we might not use, you know, these, right? But we definitely are familiar with our exocyclic double bond. If we have that, that's a 5, etc. All right, so to finish off, I'd love if you could attempt this question. A compound known to be a substituted cyclohexanone derivative has lambda max of 235 nanometers. Could this compound be a conjugated dienone? That is, you know, this functional group. Explain. So that is part A. Part B says, for this compound, how many nanometers must be accounted for by substituents? That's part B. Part C says, assuming that the substituents attached to the conjugated system are alkyl, what are the possible structures for the chromophoric system? Show alkyl substituents as R groups, right? So please try to attempt this question when next I see you. All right, that's it. Thank you so much for watching, and see you next time.